Alright, in this problem we're looking at a double Attwood machine. Now a double Attwood machine is basically a pulley with a smaller pulley attached to it, so they have two different radii, and you have one mass hanging on the outside pulley whereas another mass is hanging on the inside pulley. Now in this particular question we'd like to know how big of a radius should the inside pulley have in order to keep both pulleys in static equilibrium and basically keep our system in static equilibrium. Now to do that we have to look at some of the dimensions going on, so let's go ahead and look at what's going on with the sizes of the pulleys and masses. Mass 1 is 4 kilograms because there's 4 blocks. Mass 2 is 6 kilograms because there's 6 blocks. Radius 1 is actually 3 blocks, which means it's 0.75 meters. Radius 2, it looks to be 2 blocks, but again, this is about where would you put the object, not what does it look like when it's drawn. It actually is going to be a question mark until we can actually do the math to find out. Now, how do we deal with a double Attwood machine? It's not like a plank. I mean, it's a pulley. So how would you deal with that? Well, first, let's draw it. It's the simplified version, 2 circles. But then I recognize and remember something. This thing is going to stay in static equilibrium, meaning it's not going to move. So I could do a little trick. I could make it a plank. The plank would be one end would be right there on the smaller radii of the inside pulley, and the other end would be on the other radius of the bigger pulley. And then I just attach forces. There'd be the force of the weight hanging on the left and the force of the weight hanging on the right, which is the smaller pulley. There'd be the pulley's weight itself, and also any force that's holding that pulley system from falling down. That would be the support force. And as far as distances go, we really only have 2, radius 1 and radius 2. So that's the simplified drawing. So to label it, not much in labeling it. Now let's kind of move on to solving the problem. Now, in order to do this problem, we have to obey the physics concepts. And that's, first of all, the concept we're looking at is static equilibrium. And the first condition is net force has to equal 0, and second condition is net torque has to equal 0. The net force is fairly simple. It's the supporting force, whatever that may be, and that's opposing every weight that's attached to that supporting force. So basically the weight of the pulley and the weight of the 2 weights hanging off of the pulley. Now, the torque, on the other hand, we still want to pick a pivot point. I would not pick a pivot point that was away from the normal force or the weight of the pulley, because I don't know what those are. I would pick the pivot point to be at that location. 1, it makes logical sense, and 2, it gets rid of the normal force and the weight of the pulley as being a possible torque equation that we'd have to deal with. Now, once that's done, we can write our torque equation, which is really simple. M1g times R1 minus M2g times R2. Okay. And that's kind of the equation. So let's remember not to put in numbers. There's not much of an equation to put numbers into. Now let's do some algebra, and it's going to be fairly simple. It's like 3 steps. First step is to arrange the equation so that we have terms on both sides, not a 0. And then the next step is to recognize that there's g's on both sides, so they have to go away. And the final step would be to get rid of the r, or get the r2 by itself. In other words, get the mass 2 on the other side. There's our final equation. And well, I guess we're at the point where we put numbers in. And again, that's fairly simple. We wind up with 4 times 3/4, which is 3 over 6, which winds up going down to 0.5 meters, which is pretty much what the drawing looks like. Here's the important thing to remember. This double Attwood machine looked kind of scary at first in the sense that it wasn't the planks that you've been used to looking at. But because it's in static equilibrium, I can say that word, it can be simplified back to being into that very simple plank-like way of looking at things. So that's how you do the double Attwood machine when it's in static equilibrium.